In the last video, we got some practice working with intensive variables and seeing why they might help us work with some calculations. In this video, we're going to look at reservoirs, one of the most powerful tools we have for changing the kinds of things that we can do to thermodynamic systems. First, let's start with the definition. We actually have two distinct definitions that we need to do to make this make sense. So let's start with one of them. A thermal reservoir is a simple system with entropy a linear function of internal energy. Let's see what that looks like. In this case, we have S is equal to some constant of proportionality alpha times U plus, I'll use capital B here. So here, alpha is a constant of proportionality, and that constant should be intensive, since U is extensive, and we want S to be extensive. On the other hand, B should be extensive, which means that this B can only exist if this system has some work coordinates for us to work with as well. All right, wonderful. Second definition. A reservoir for generalized volume VI is a simple system with entropy proportional, a linear function of VI. So these are mostly very similar. The only difference is that in the thermal reservoir case, we have a linear function of internal energy. And in the reservoir for generalized volume case, we have entropy a linear function of VI. All right, wonderful. Let's use the thermal case and we'll see what we get out of this. So in particular, I want to see what the temperature is in this case. So again, we're going to set S equals to alpha U plus B, where B cannot depend on U. That implies that partial S partial U is simply equal to alpha. And this gives us some important information because this is equal to 1 over T. In particular, it means that S is equal to U over T plus B. Since B is constant with respect to U, that means that for every state in this state space, the temperature is the same, T. Let's also look at pressure for that particular case. So we're going to say that this is ordinary pressure, excuse me, and so the generalized volume that we'll use is just the ordinary volume V. All right, in this case, I'll just use the same names for these constants. So we'll have alpha times V plus B. In this case, we get partial S partial V is equal to, well, again, it's just alpha, since B can't depend on capital V. Furthermore, we know that that implies that P is equal to alpha times T, capital T. Wonderful. So in this case, we get that S is equal to, well, if we move the T over, then we get PV over T plus B. All right, I think that this gives us a lot to work with. And in particular, I think that the next obvious question is how do we actually get one of these reservoirs? We have this as a sort of abstraction, and it may be that it helps us do some calculations. In particular, I think maybe it's not too hard to see why it would be useful to think of systems that have a constant temperature or a constant pressure at every point on the state space. Um, Although I should clarify that. In the pressure case, we only have constant pressure at every point on the state space with the same temperature, since this expression depends on T. In any event, let's see how we would actually get um, one of these reservoirs. And we'll do that using the ideal gas. So I'll just remind you that we have, for the ideal gas, S equals NKB log, and I'm going to change something actually a little bit to comport with what's in my notes, which is to call the constant proportionality that we have been calling phi sigma instead. So I'll say sigma V over N, U over N to the 3 halves, plus 5 halves NKB. And what we're going to do is take a thermal join of two such systems, or we'll call the systems A and B. Wonderful. We already know what happens in a thermal join. We've done that already. We know that T is equal to 2/3 U over NKB, which implies that after the end of the join, we'll have UA prime over NA equal to UB prime over NB. Okay, good. So now the question is, under what situation or under what case will UA change only a little bit? Let's rewrite this in the way that we did in the last video. UA prime is equal to NA over N total of U total. Now this doesn't say anything in particular about UA, but we can rewrite this U total in terms of UA. So NA over N total, UA plus UB. And this gives us a pretty good condition under which we could get that UA prime is very close to UA. So we would need, let's say, NA is much greater than NB, and UA is much greater than UB. And these are for the initial values, or I should say for the energy, that's for the initial value. For the particle number, obviously, things don't change. So what we get out of this at the end, if we plug in these two limits, is that UA prime is approximately then equal to, well, NA over N total is approximately equal to 1, and then UA plus UB is approximately equal to UA. So these, again, will be approximately equal. All right, very good. So now let's plug back in our assumption that UA will be very close to UA prime back into here. So in this case, we can Taylor expand around UA and see what the entropy is. So let's do that. We know that at UA, at our initial value, we get SA is equal to NA, KB log sigma VA over NA, UA over NA to the 3 halves, plus 5 halves NAKB. But we actually want to evaluate SA at UA prime. So we want to stick in, using a Taylor series, the first order term, which will depend on delta UA prime, since we're expanding around that point. To do that, we need to take a U derivative of this, and then evaluate it at UA, then multiply by delta UA. So doing that Taylor series, we'll get precisely DSA DUA, which, again, we would have the NKB come down, then we get log of U to the 3 halves. That would give us 3 halves NKB over UA. But remember that we'll have a delta UA in the numerator. Okay, so now maybe it doesn't look like it, but this is precisely in the form alpha times, let's say, delta UA plus B. Now, remember that we always have the freedom to choose our 0 point of internal energy. And so that should be familiar from, for instance, classical mechanics, where we can set, for example, the height at which we decide that the potential energy is 0. That doesn't turn out to affect the dynamics at all. We can do the same thing here. So if we move our 0 point such that delta UA is just equal to UA, or equal to UA prime, then we have exactly the form that we wanted. So what do we learn? We learned that we can approximate a reservoir by a system which is much larger than the system to which it's being thermally joined. And I'll say a thermal reservoir. If it is, and I'll put in quotations, much larger than the system to which it is being joined. Effectively, we need that the number of particles of the reservoir system is much greater and the energy, internal energy, is much greater than the system to which this reservoir is being joined. If those conditions are both true, then we find that the internal energy of our reservoir system doesn't change enough that we get a nonlinearity, that we effectively get the second order term in this Taylor expansion. So often, when we're talking about doing calculations with reservoirs, we will pretend that we have a perfect reservoir to make our lives simple, to make the computation easy, and because then we can talk about a truly constant temperature. But if we wanted to actually approximate one in real life, we would need to do something like this. Now, I'm going to clean up part of the board, and we can look at one example in which we can use reservoirs to make computations a lot easier and to see some new physics. Okay, let's now look at a mechanical join, and we'll figure out a couple of things that are true in this case that maybe we haven't seen before. So we'll say that our system A is our reservoir. Again, it's a mechanical reservoir, so it will follow this equation here. So we'll have SA is equal to PA times VA over T plus B. Now I'm going to leave T as just a constant. And that's because I'm going to say that our system B is an ideal gas, which also has also has temperature T. So SB, I'll just say, is given by the Sacher-Tetroda equation. Which I don't need to write, but in particular, we have PB, VB equals NB, KB, T. Okay, wonderful. So what happens now when we take a mechanical join of these two systems? We know that their pressures will be equal. The problem is, or maybe not the problem, but the fact of the matter is that PA is constant at every point in A's state space that has temperature T. So there's no other pressure that they could go to. What happens afterward is that B's pressure becomes PA. So we can say PB prime is equal to PA, which then we know is equal to NB, because N doesn't change, KBT, since T doesn't change either, over VB prime. Okay. Next up, let's think about the difference in the volume of B and the difference in the volume of A. We know in the process that the total volume has not changed. Now we can invert this equation to get some more information. So we know VB prime is equal to NB KBT over PA. And conversely, just writing this equation again with that inversion, we get VB is equal to, well, that's just going to be NB KBT over PB. And what all of this implies is that the change in VB is equal to NB KBT times, well, because it's going to be this minus this, 1 over PA minus 1 over PB. Notice that this could be positive or negative, and it could be arbitrarily large or small. That means that the reservoir is giving up as much volume as it needs to in order to equalize the pressure to PA. It also could accept as much volume as it needs to in order to get the pressure to PA. This makes sense thinking about the term reservoir. What is a reservoir in real life? Well, it's a large body of water, usually artificial, that we dump water into as a sort of holding tank. We then could think of a generalized VI reservoir as a sort of holding tank for the quantity VI. In this case, we can think of the mechanical reservoir or the V reservoir as just being a holding tank for a volume. It contributes as much volume as it needs to. And with that, I think we're at a pretty good point to go and look at some different systems and take a much broader view of the field. I don't want you to get the sort of confusing idea that this whole field is just about studying the ideal gas. We'll get to that in the next lecture. Until then, thank you so much for watching. Bye-bye.